do. So I'll probably be working on that tonight is the plan, but I hope you guys are doing well with the studying so far. If you haven't tried that sample midterm yet, I would suggest doing that by today at some point to take a look at some of those questions and see how it goes. And hopefully that'll inspire you to ask me more questions if you have any. I do have office hours later tonight, and also tomorrow in the morning, I'll get here at least a couple hours ahead of the exam. So if you have any last things to ask me about, I should be around. I'm glad to help you out with that. The review packet is also worth going through. So there's all of the sort of a summary of the main points of what we covered. Make sure you can check all those off. Say, I know what this is, I know what this is, I know what this is. And then even more than that, make sure you're able to do the things in the packet that are listed there. So there's some skills, basically a list of skills that you should have, and then also some results you should be able to prove. So somebody was asking me about that. Do we need to be able to prove the stuff that says I'm supposed to be able to prove? And the answer is yes. That's what it's in the packet for. So, I'm probably not going to ask questions that are super long-winded. I'll try not to do that, or if I do, I'll try to break them down into pieces for you. But nonetheless, things that are relatively short and crisp definitely should be able to do. I won't ask true-false questions, but if I ask you, is this function continuous at 0, for example, that's really a true-false question. It's a yes-no question. Any answer will need to be justified, right? The justification will be really what you're going to be graded on. You could have the wrong answer, but then have a lot of correct, relevant stuff written down. I'll give you points for that. Or you could have the right answer with nothing written down. I won't give you points for that, right? So it's very important to try to explain what are the relevant pieces of information, even if you're not quite sure how to do the problem, but you can sort of tell that this is a problem that has to do with, I don't know, using the squeeze theorem or something, right? So if you see something like that, it would be helpful, I think, to write that down. Even if you're not quite sure how it works, the fact that you realize what skill set or what tool is really needed, that can be really, really helpful. Yeah, and then as I've been telling people, I will almost certainly allow you to take something home and try to be real wise about your choice with that. You don't want to, you want to take home something that's worth a few points, but that you really think you could do a better job at home than what you're doing right during the test, as opposed to something that, you might as well just write it down during the exam and then take something else home. So that'll be up to you guys to use your best judgment about that. But yeah, I have not written the test yet, unfortunately, so I can't say for sure exactly what that's going to look like. So yeah, so I guess that's all I really have by way of sort of general overview. I think I'm going to continue basically picking up where I left off. On the first review session, I did 8 problems, and I have 8 more problems that I didn't get around to last time. I was really happy with the 8 that we did last time. The ones that I've got for this time, some of them are maybe a little bit not quite as exciting to me, but I'm going to do as many of them as I can anyway, because I think it's still going to be helpful. So if that's okay, are there any questions before we jump in here, guys? Not so far? Okay. If not, then let's try some practice problems here. So this is going to be review number 2. And I'm going to math 350. And we're talking about midterm number 2. And so I'm going to just pick up the numbering with where I left off. So this should be number 9. And here's the one I want to do. So for number 9, I'm going to let x1 be equal to 3. And for n greater than or equal to 1, I'm going to define xn plus 1 to be equal to the natural log of the quantity 1 plus xn. And what I want to do with this is prove that xn converges. Okay, and we always want to pay attention to whether they're asking us what it converges to or not. This one is not asking for that. It's just asking us to prove that it converges, so we don't have to actually find the limit. Because sometimes that makes a difference in sort of how you're going to approach this. Okay. Does anybody have any suggestions for maybe what we might want to do first when we first see a problem like this?
See if it's increasing or decreasing.
How are you going to see whether it's increasing or decreasing? By trying to plug in some numbers. By the way, can you guys out there in Zoom hear me okay?
Yeah, we can hear you.
Okay, just making sure. It always wants to make my window really small, and I don't want that. 1 second here, I'm gonna technical difficulties, I guess you could say. Guess I'll do it like that. Okay, I can't see you guys out there in Zoom, so if you have questions in Zoom, please use your microphone to get my attention.
Yeah.
but
So I do have one question.
go ahead.
So I'm already assuming that we're gonna be using MCT. Does it matter what order, like how we approach the problem? Like if we find how xn is bounded first and then find out it's monotone, or if it's monotone first or bounded?
It doesn't matter. By the way, is that what you guys all thought about as well, the monotone convergence theorem? What is the tip off that you might want to use the monotone convergence theorem here?
Recursive, if it's recursive.
It's a recurrence relation, and
We don't have to prove what it converges to.
we don't have to prove what it converges to, which the monotone convergence theorem doesn't tell us what it converges to, but especially the fact that it's a recursively defined sequence. And we've seen a lot of examples of this. So Danny, to answer your question, we do not have to do these steps in a certain order. We can prove that it's monotone first and then prove that it's bounded, or vice versa. There is a slight advantage, though, to proving that it is monotone first. Because if you know that the sequence is monotone increasing, then it will be bounded below by x1. And if it's monotone decreasing, it'll be bounded above by x1. So you'll be able to get one of the two sides of the sequence bounded if it's monotone just by using the first term. So I generally will start with whether this thing is monotone or not, and then do the bounded second. Does that make sense?
Yeah, that makes sense. Yeah.
Okay, great. So yeah, so I like all the reasoning that we gave here. Let's see if we can apply the monotone convergence theorem. And of course, you should be able to state this theorem and even prove it, I would say. I would suggest that if you haven't looked at the proof of this monotone convergence theorem lately, that it might be worth just reminding yourself how that goes. So we're going to try to apply the monotone convergence theorem. But going back to the very start of this conversation, Lindsay was suggesting we just try to figure out whether it's monotone initially by just plugging in some values. You know, it can never hurt you. This won't get you a lot of mileage, but at least just writing down a few terms might give you a sense of what kind of numbers you're working with. Now, you won't have a calculator to figure these things out, but you might, this one, a calculator might actually be helpful. But we don't need a lot of terms to figure this out. Like, so for example, x2 should just be the ln of 1 plus x1. And so this is going to be the natural log of 4. Now, when you're comparing 3 with the natural log of 4, you might have to think about that for a minute. Remember that, you know, if you're comparing these two numbers, you could just exponentiate both sides and say, well, because the exponential function is an increasing function, so how would e cubed compare with 4? Becomes a little more obvious, so this is 2.7.
Sure.
Maybe take 2.7 times itself. it's, even if you just take 2.7 squared, it's certainly more than 2 squared. So this is gonna be bigger than this, so I would expect that to be bigger than that. So that means that x2 is less than x1. Now, if we don't know any more than that, I would expect people to be able to do that without a calculator. Now, knowing that, I'm already a little nervous to try to do the next one. X3 would be the ln of 1 plus the ln of 4. Okay, that's definitely getting a little bit harder to do in my head. But even just knowing this much, if you're really confident that Dr. Anna is probably asking us about the monotone convergence theorem, I would suspect that this is monotone decreasing, right? And we can make that as a claim and then try to prove it. So the claim is xn is monotone decreasing. And what is the main method that we use to prove something like that?
Induction.
Right, we would probably try to prove that by induction on n. So proof by induction on n. So I would probably start with just the base case. The base case would be comparing x1 with x2. So when n is equal to 1, then x n plus 1, which is just x2 in this case, is the ln of 4, and that is less than 3, which is x1. Okay, so in this case, the x2 is less than x1, so we can put a check on that. Fairly self-explanatory here, what's going on. So that's for n equals 1, and now let's do this. So that's what we call the base case. The base case is n equals 1. So now we get to the induction step, and so what we would do here is we would assume that xn plus 1 is less than xn, and then what we would look at is, well, what about comparing xn plus 2, which would be the next term? I want to compare that with xn plus 1. So what can we do in terms of writing down xn plus 2? Go back to our recurrence relation, exactly. So here's our recurrence relation. And if I want to know what xn plus 2 is, I just have to jack the subscripts here up by 1. So I take the xn plus 1, I jack it up to xn plus 2. And on the other side of the equation, we would have the ln of 1 plus x sub n plus 1. All right. Now, from there, what we can do is we can use our assumption. We know that xn plus 1 is less than xn, so that should mean that the ln of 1 plus xn plus 1 is less than the ln of 1 plus xn. That is because, I'm just going to make a quick note here. This is since the ln of x is an increasing function. I mean, if you look at the graph of the ln function here, the bigger my input, the bigger my output. So in this case, the smaller my input, which is this input, is smaller than this input, so the output on the left should be less than the output on the right. So be careful about that. If the function is decreasing, if the function was actually decreasing, then if you plug in a bigger input, you would actually obtain a smaller output, right? But this function is definitely increasing. So if we plug in 1 plus xn plus 1, we should get something less than when we plug in 1 plus xn. And this is just xn plus 1. We'll put a little check on that. Look okay? So that's the induction step. And we did our base case, so this is the proof of this claim. Okay, so it's a monotone decreasing sequence. And the next part of it, as Danny reminded us, is we also have to prove and claim that xn is bounded. We have to show that this is also bounded. And that means bounded above and bounded below. But since we've already proved that it's monotone decreasing, we already know, what do we already know?
Bounded above by x1.
It's bounded above by x1. Okay, so since we can write that down, since xn is monotone decreasing, the sequence xn is bounded above by the very first term of that sequence, which is just x1. Okay, so it's bounded above by x1, and now the question is, well, what's it going to be bounded below by? Now, that might not be clear because, well, what I'm plugging in here looks to me like it's always positive, unless somehow the xn's could dip negative. But I don't think that can happen because the ln of anything that's more than 1 is always positive. So x1 was already more than 1, so you're plugging in things here that are positive, and therefore you're going to get things, you're evaluating the ln on values that are bigger than 1, which means that the output of the sequence will then be greater than 0. See what I'm saying? Right, so this is 1, 0 is right there. So as long as what I'm plugging in is to the right of 1 into my ln function, my output is greater than 0. So we certainly could claim, let's make this as a subclaim, we certainly could claim that xn is bounded below by 0 if we wanted. At least we would expect that to be true because we're taking the ln of numbers that are more than 1, and so the output of the ln function is always more than 0. Okay, so let's just try to prove this by induction. Let's just prove this by induction. So this is clear for n equals 1 because they gave us, that's the base case, they gave us x1 is equal to 3, so that's obviously greater than 0. And so now let's do the step, the induction step. This is where we're going to assume that we already know that xn is greater than 0. By the way, you could use greater or equal to. Doesn't make a difference here. So it doesn't matter whether that's strict or not. But if I do that, if I assume that xn is greater than 0, then see, I think we actually already did the analysis of this in just thinking about the lower bound, right? So xn plus 1 is the ln of 1 plus xn. Well, that will be greater than just the ln of 1. Again, this is also since the ln is an increasing function. So same justification again there. So the ln of 1 plus xn should be greater than the ln of 1, but the ln of 1 is 0. So xn plus 1 is also greater than 0. Make sense? Okay, and then just don't forget to write one last sentence then. Once you've shown that it's monotone and bounded, then you should wrap this up by just concluding, thus, by the MCT, xn converges. I wonder, how come you think it is that they didn't ask you what it converges to?
Sounds messy.
Sounds messy. Yeah, exactly. Let's just see. I'm just curious. I wrote this question long enough ago, I don't remember. But you know how you would do it, right? If it converged, then what you would do, to find the limit, we're not going to do it here because if it was possible, they would have asked us to do it. But to find the limit, what you would do is you would just assume that xn does converge, let's say, to some number alpha. Right, and in that case, then if we look at xn plus 1, which is the ln of 1 plus xn, that should converge to the ln of 1 plus alpha. But xn plus 1, of course, also converges to the same thing that xn does. So this would converge to alpha. So what we would get is that alpha is equal to the ln of 1 plus alpha. And without a calculator, I think this is gonna be a little bit much. We can exponentiate both sides. So there's the relationship between alpha and e to the alpha showing up. And the goal would be to solve this for alpha. Well, it's not an easy equation to solve by hand. Okay, you can plug that into a computer and it'll do it for you, but there is not a simple answer here. So that's why they're not asking you to prove what the limit is. Because it's hard to get it. But it's a nice problem.
By they mean you.
But yeah. Actually, I probably didn't write this question, so it probably is somebody else that originally decided this was gonna be too much. Okay, so that's a nice, what I'm really excited about with something like this is that you recognize that it's the monotone convergence theorem, okay? So if you recognize that it's the monotone convergence theorem, but you just, either you don't have time or you're just kind of in the fog about how to actually do it, I would recommend one of two things. You either decide to take it home. Okay, can't do it on the fly, take it home, that's an option. The other option would be to just write down what you know as best as you can. Okay, this is obviously going to be an application of the monotone convergence theorem. Here's what I need to prove. I'm blanking out on how to do it, but I want to tell you what I know. And in that case, you would get some partial credit for it, depending on how much you actually wrote down would affect how much partial credit. It could be up to as much as almost half, I suppose. So you have to make a decision. Well, do I want to take half credit for just sort of giving the outline, or do I want to take this home and just nail it 100%? And that might depend on how the rest of the test is going. So you just have to, in the moment of the exam, you can try to figure that out.
Doctor, and I remember doing a bounded part of the
Yes.
proof. We always prove. Do we have to prove first that it's bounded, and then where it's bounded at? Or what is it always?
You're always proving that your sequence is bounded by giving me
where?
Okay. Yeah, and this, what if I had said xn is bounded below by -1? That would have also been correct, right? It wouldn't be wrong, so you would then just prove that claim. There isn't necessarily a unique right answer here. But you want to put something here that's correct, but also provable, okay? So if you put a -1 here, I mean, the base case is pretty clear, but then I don't know how the rest of this would go. Because if we put a -1 there, then instead of replacing the xn with 0, we would be replacing it with -1, and 1 + 1 is 0, and the ln of 0 is like -infinity. So that wouldn't have worked so well. It would not have been wrong. It would not have been wrong, but I would have had trouble doing this step here, making the induction work. So you wanna pick, so that's why you can't just be sloppy with it and say, oh, I know it's bounded below, so why don't I just pick -1,000,000? Because that I'm sure that'll work, right? Because you might have trouble running the induction with -1,000,000 plugged into your work, right? So you wanna try to pick the lower bound that makes the most sense relative to what the sequence is and what kind of values you can calculate. I know I can calculate the ln of 1. Okay, so in that sense, it's kind of a good choice. Questions in the Zoom group, or anybody in here got a question? I can't tell exactly how people are doing with it, but hopefully it's making some sense. Okay, if we're good with that, let's do something else. Let's I guess I'll continue on the theme of sequences for a moment. Let's go to number 10 here. So let's define a sequence again. This time xn is going to be 3n squared plus 7n plus 5, all divided by 8n squared plus 3n. Okay, so that would be for all n greater than or equal to 1. And what I want to do on this example is I would like to prove that xn, sequence xn, converges again. Okay, so similar objective, but with a different kind of sequence. So I have to think about all the tools that we have and which one or ones would be the right things to use here. Do you think maybe the monotone convergence theorem would be good for this one? I don't think so. The monotone convergence theorem does, I mean, you could try it. You could plug in x1, x2, and x3 and see if you could get anywhere with that. But you know, when you're thinking about doing induction and you're gonna like compare, so if you're gonna use the monotone convergence theorem, then you have to compare xn plus 1 with xn, right? That's because you're checking that it's monotone. And that means you're gonna replace all these n's with n plus 1s and compare it with what's here right now, so you can see what a mess that would be, right? Okay, so I'm not wild about trying to do it that way. I'm not gonna say it absolutely wouldn't work, but it would be probably not my first thought. Okay, see, half the battle on these problems, guys, is figuring out which tool to use. Right, we have the definition. You use the epsilon and not definition. We've got the monotone convergence theorem. What else do we have? Definition. We have algebra. You know, just manipulate this thing a little bit. So, you know, just point out here. Let's just try that. So, in case you couldn't hear in the Zoom, Lila suggested that we just divide through by n squared, and I see no harm in at least trying it. Let's just go ahead and do that. So we divide every single thing on the top and on the bottom by n squared. Just make sure your algebra is sharp. Be real careful with it. Okay, does that inspire me any further in what I could do?
Limit theorems.
Start applying the limit theorems. Okay, so that's another tool, right? The fact that limits respect addition, subtraction, multiplication, division, you know, as long as the denominator is not 0. Now, I could not have used the limit theorems with the sequence as it was originally presented, because as n goes to infinity, all of these individual, well, not all of them, but everything except the plus 5 doesn't exist. Well, it's plus infinity, to be more precise. And plus infinity technically doesn't exist. I don't do well with infinity plus infinity. These are all plus signs, but if there were minus signs in there, it'd be even less obvious what to do with that. Because infinity minus infinity is one of your classic indeterminate forms, like you don't know what it's going to. But after you divide through by n squared, now you've got 1, 2, 3, 4, 5 individual sequences, all of which we know converge. So in fact, we know, and you can just use this fact, guys, we know that the sequence 1 over n converges to 0. So by the limit theorems, right, xn would converge to 3 plus 0 plus 0. I guess I'll say, actually, let me write it out a little bit better. Sorry. I don't want to jump to the answer too quickly. I'm not saying I would not accept it, but I would probably say this converges to 3 plus 7 times 0 plus 5 times 0 squared. And then on the bottom, I would put an 8 and then plus 3 times 0. So I'm using the fact that we can pull the 3 out as a constant, the 7 out, the 5 out, those come out as constants. 1 over n squared converges to 0 because 1 over n converges to 0 already. So that's why I put 0 squared here. If you didn't write all that out and you just wrote 3 plus 0 over 8 plus 0, I'd take that. But it's just a little nicer when I see all of the details spelled out, and now you get your answer. Okay, so by the limit theorems, which is proposition 3.2, I want to say, or 3.7. It doesn't matter. I don't make you guys memorize those numbers, but I'm always just curious if I have it right. No, it's got to be 3.7. I'm sorry, no, it's theorem 3.2. Theorem 3.2. So if anybody wants to look that up just to make sure they know what all those theorems say, that's the reference for you. Theorem 3.2. Okay, great. So far, everybody okay? All right, let's press on. go to number 11 here. Okay, so this is kind of an interesting question. To prove that the limit as x approaches 2, so I'm now going to go to chapter 4. To prove that the limit as x approaches 2 of the square root of the quantity x plus 2 is equal to 2, you are tested. You are tested with epsilon equal to 0.1. Okay, so then the question is going to be, what is the largest delta? What is the largest delta greater than 0 that you can apply the epsilon delta definition of a limit to? What I like about this problem is that it actually is going to involve some number crunching in the midst of all of it, which we don't normally get to see. So it's a little bit of a curveball, you could say. Haven't done a problem quite like this before, but it really is just a matter of making sure that you understand the epsilon delta definition. I might recommend, if you see this question, maybe I would have already asked you what the epsilon delta definition is in a previous part. If not, I would probably recommend writing it down, right? So let me just do that here, just so we have it on the board. The limit as x approaches c of f of x equals L. The definition of that by the epsilon delta notation is, for all epsilon greater than 0, there exists a delta greater than 0 such that if 0 is less than absolute x minus c is less than delta, then absolute f of x minus L is less than epsilon. So in blue, I just reminded you of the definition, and in this case, what we're looking at is the function f of x is the square root of x plus 2, right? And the L value is 2. And in this case, they're giving us, and the c value is also 2. Just kind of figuring out what the numbers are that we have. And then they gave us epsilon of 0.1. So the way these proofs normally work is you let epsilon greater than 0 be given, and then you find the delta. They're basically asking you that here as well, except with a specific epsilon in mind. So instead of writing let epsilon greater than 0 be given, the thing we're going to want to do here is just go straight to the scratch work. Because normally that's what you'd do. You'd let epsilon greater than 0 be given, and then you would do the scratch work to solve for the delta. And so let's focus on that scratch work. So for the solution now I'm ready to actually think about how to solve this. The scratch work is going to entail looking at absolute f of x minus L less than epsilon. In this case, epsilon is 0.1. I'm just going to put the 0.1 in there. And then that's going to be if and only if I'm going to substitute my f of x is the square root of x plus 2. My L value is 2. And all of that less than 0.1. Okay. And ultimately, if I want to figure out the delta part, I need to come up with, absolute value of x minus c. In this case, c is 2. And so I don't see x minus 2 anywhere in the work that I have there. So we're going to have to do some more stuff here to figure that out. Does anybody have a suggestion where we could kind of go from here?
Do it on both sides.
Do what on both sides?
Negative 0.1.
Oh, unwrap this as, okay, so we could say this is equivalent to negative 0.1 less than, So getting rid of the absolute value bars, which seems like a reasonable thing to wanna do here. So we just unwrap that with negative 0.1 less than square root of x plus 2 minus 2 less than 0.1. Okay?
Good.
And now what?
Add the 2.
Add the 2 to everything, okay, so, and all of these are, so far, everything is reversible, right? You have to be careful about that, if something's not a reversible step, I don't wanna be using a double arrow. Okay, so we're gonna get, if I add 2, I get 1.9 less than the square root of x plus 2, less than 2.1. So far, so good. I still don't see my x minus 2 anywhere, but we're also not done yet, so let's keep at it. Might be a little more room, I'm gonna just continue my scratch on this side over here. Continued. This whole problem is all about the scratch work part. It's really what we're practicing here. Any suggestions on how to play with that?
Square it and subtract 4.
Square it and then maybe subtract 4. Okay, let's start by squaring it. Does anybody know what 1.9 squared is? I do.
1 to the 2.
3.61.
Sees with the square.
Somebody's done this problem before. Less than x plus 2, less than, and 2.1 squared is 4.41. I had a grade school teacher who made us memorize the first 30 perfect squares, and she would quiz us every day we'd go in, and she'd give us 5 problems and she'd give us 5 seconds. And we had to like just answer, and she'd make us put our pencils down. She was like a drill sergeant. She was like super strict. If you didn't have your pencil down after 5 seconds, you were in trouble. You have to stay after school. Anyway, so I learned these pretty well. I think I got it right. Anyhow, so now you want me to subtract 4. Okay, if I subtract 4, I'm gonna get negative 0.39 less than x minus 2 less than 0.41. I guess the reason for subtracting 4 is so that you can get your x minus 2, which is really x minus c, that we need right here to figure out what our delta is. Okay, is everybody with me so far? So the question is then, what is the largest delta that we can actually get away with based on this? And I'm wondering if anybody has any thoughts about that.
0.41. Anything up to that.
So let's just think about it for a second, if we use a delta of 0.41. So, and then we'd have 0 here, right? So if this was what we had, then what this would mean is that when I remove the absolute value bars, whatever we're saying has to be true for this whole range of x values. Okay, except for x equals 2, we're removing x equals 2 here, right? But if, let's say that x minus 2 was negative 0.4. Okay, that satisfies this constraint, but can I run the scratch work backwards if x minus 2 is negative 0.4? No, because negative 0.4 is outside of this window, right? This window goes from negative 0.39 up to 0.41. So this is part of what this question is getting at is, like which endpoint sort of controls this decision? And the answer to that is you always want to choose the smaller, this is why I always take a min. If you have like a delta 1 and a delta 2, you always take the minimum of those deltas because then you're guaranteed that everything can be applied. So if I look at this, I say, well, maybe delta could be 0.41 or maybe it should be 0.39. Like which one is it? The safe answer is actually 0.39. And in fact, the correct answer is 0.39 because if we try to let delta be 0.41, we get some x values here for which we cannot retrace the scratch work backwards. Okay, so I'm going to just state that now. So based on this, we need 0 less than absolute x minus 2 less than 0.39, and so this becomes the best delta that we can get away with. As long as, because if delta is 0.39, right, then what you're going to have is that x minus 2 is between plus and minus 0.39, and those x's all fit into this assumption here, and I need to have a filter. They fit into this constraint here, and from here, then we can run the scratch work backwards and get our conclusion. Does this make a little bit of sense? So yeah, it would actually be 0.39 in this case, so. When in doubt, use the smallest delta. I guess that's maybe the punchline there. Okay, I've done that one, I've done that one. Okay. Super, super.
So there's nothing to prove in this one. The
No,
scratch work
this
is,
isn't really a proof, yeah, you're just doing the scratch work. I mean, the scratch work, a lot of times, the scratch work is the main part of the work. I mean, the only thing we didn't write down is let epsilon greater than 0 be 0, let epsilon greater than 0 be given. And we didn't write down, retrace the scratch work to get the answer. That's about the only part of the proof that's not here. Yeah, so that's kind of an interesting example. There wasn't anything like this in the book, but it's a nice problem to practice on. Any questions out there? So far, so good. Okay, well, we're cruising right along through these. Let's go to another problem. All right, let's go to this number 12. This is gonna have a couple of parts. I just want to compute the limits here. Compute the limit if possible. I guess I'll add that. And so for part A, we're going to take the limit as x approaches -2 of the fraction, which is x cubed plus 7x squared plus 10x, and the denominator is x plus 2. So, do I have any thoughts about what to do with this?
back to the top to x times x plus 2 times x plus 5.
Okay, so this is actually factorable. So let me just pause for a minute. Of course, we could just says compute the limit. It does not say prove it from the definition. If I wanted to prove it from the definition, I would have said that, and then you would have to do the epsilon delta definition of this. But since I just said compute the limit, of course, it's going to be with work shown. You can't just do it without showing any work. But we are allowed to manipulate this a little bit, right? We're not being guided too strongly on it. And actually, this is pretty straightforward. If you factor the x out of the numerator there, then you're left with a quadratic, which I think factors as x plus 5 times x plus 2. Yep, like that. Okay, so far, all I did was factor the numerator, but I didn't do anything else. Now what? Let's see, sorry.
Cancel the x plus 2 and the numerator and the denominator.
Okay, we can cancel the x plus 2. Why are we allowed to do that?
They're the polynomials.
They're polynomials, but there's something else I'm looking for. But why can I mean, obviously, if I have something like this, which is undefined, I'm not going to cancel and say, oh, that's equal to 5/4. So there's a little bit more to it than that.
Is it because of the limit rules or each individual limit? You're basically studying them up.
So I could imagine using my limit theorems here and say, well, I'm going to take the limit of each piece, right? The problem is if you use the limit theorems in the denominator, you'll get -2 plus 2, you'll get a 0 on the bottom, right? And the limit theorem about quotients is that, yeah, you can take this limit by doing the numerator and denominator and dividing them as long as the denominator is not 0. but in this case, it would be 0. And so I'm not confident about actually using the limit theorems for this. But I'm looking for the real reason why I can cancel the x plus 2.
Let y equals x plus 2, and you got y over y.
That's just a change of notation.
It's still just algebra.
Yeah, it's still the same thing, it's still canceling something. There's something else I'm looking for here. It's about limits as x approaches -2.
Because x doesn't have to equal them.
Not only does it not have to, it cannot equal -2, right? Remember in the definition of this limit. We have 0 is less than absolute x minus c is less than delta. So the point is x is not going to be equal to c. In this case, x is not going to be equal to -2, which means you have something that is not 0. So you can cancel, so I'm gonna add that here, it's a little bit of justification. Since x plus 2 is not 0 when x approaches -2. Okay, so that's the point. Okay, so the limit as x approaches -2 means that x won't be equal to -2, so I'm perfectly good to cancel that term away. Okay, and now what? Now we can just plug this in, so this becomes -2 times -2 plus 5, which becomes -6. And what would be the reason that we could just plug it in?
It's a continuous function.
Because it's a continuous function, it's actually a polynomial. And because it's a continuous function, then we know that the limit of, by the huge remark, right? So by the huge remark. Dr. Annan's huge remark from class, again, don't have a good reference for it other than that, but by the huge remark, since x times the quantity x plus 5 is continuous. And I'll just add here, i.e. it is a polynomial. So we have a polynomial now. We did not start with a polynomial. We started with a rational function that happened to be 0 when we tried to approach the limit value. But it is a polynomial, so the limit as x approaches -2 of x times x plus 5 is just equal to what you get when you plug it in. Okay, I'm filling in a lot of justification here. I'm not saying I would absolutely have to see every last word there, but I would probably want to see some of this justified. I mean, honestly, this is a question you can ask in freshman calculus too, right? So what's the difference in 350? The difference here is just we're really justifying all of our steps very precisely. Okay, so that would be what I would hope you'd be able to do, and I might even be phrasing my question in such a way to make sure that you're going to justify those steps. Don't just decide, oh, I guess I'll just factor and cancel and plug in the number and don't have any other explanation there. There's a tendency to not write enough words down sometimes, and that's great for freshman calculus, but not so much for this one. Yeah. Okay, so that was part A. Let's try another one. Is everybody okay with this? Yeah, not too bad. Okay, let's try another one. Let's do the limit as x approaches 0 of the quantity x plus 3 times the sine of 1 over x. Okay. So again, we cannot just plug in 0 because we'd be dividing by 0 on the bottom there. Don't really want to use the epsilon delta definition of anything because that looks messy. Sometimes when I see the sine function, I'm thinking about squeezing it, Cause I know that sine can be squeezed between -1 and 1. Right, so just a bell goes off in my head, okay, for sine or cosine. We can bound things between -1 and 1, so for example, I could say that. So I'm just scribbling right now, I'm not saying this is gonna be what we do, but just so you can kind of see. What you might be thinking about, if I just kind of put absolute value bars around that, we can just chop off the sign of 1/x part, because that would be less than or equal to 1. Of course, the whole thing will be greater than or equal to 0 if we do that. But the problem is that as x approaches 3, as x approaches 0, this thing approaches 3. So it's not being squeezed properly. If this had been approaching 0, then I would have been able to say, oh, well, there's 0 less than or equal to that, less than or equal to 0, and so by the squeeze theorem, this one would go to 0. And that would have been fine. But in other words, if the problem had been this, then we could use the squeeze theorem and the answer would be 0. Right? But this +3 thing is kind of screwing it up a little bit. Now I've got 3 over here, I got 0 here, we're not really squeezing it. It's not getting squeezed properly.
But we got the rules of limits that they're both continuous, we can separate them.
Okay, so John's idea, in case couldn't hear that, the idea here is, we got limit theorems. So I could think of this as that part times, I think this is what you're saying. Times this part. Right? And now let's just be very careful. This property is true provided that both of the individual limits exist. In fact, in the review session the other day, we showed a counterexample where the limit of the product might exist without these two things existing, and then it doesn't make sense to use this result. So we would have to know that both of these individual limits exist first. And do we think that they do? You've actually seen this one in class. I'm gonna draw you the graph of it again. So it wiggles between -1 and 1. But as you get towards 0, it really takes off fast and goes kind of something like that. So does that limit exist? And the problem is that, so we have this sequences characterization of limits, you might remember. So if the limit of f of x is equal to L as x approaches C, then that would imply that for every sequence approaching C, so call it xn. So if xn converges to C, then f of xn should be converging to whatever the L is, right? But I think I can make a sequence here that's converging to 0. Let's take the easiest thing in the world, 1/n. But when I take f of that sequence, so the f of that sequence is just the sign of the reciprocal of it. This one does not exist actually. And so there is no L there. There is no L there. This actually does not exist. And I think this was actually one of the ones in the notes. So you might go back and review. I think I used this exact example where you have a sequence approach to disproving the limit exists. This was actually the fact that sine of n does not converge was actually a homework problem. And if you remember that there was a homework problem that you want to use at any point during the test, you certainly can. So keep that in mind. Sine of n does not converge. Now, what I can say about it, this is totally off topic. sine of n is bounded by -1 to 1. So it's a bounded sequence. So by the Bolzano-Weierstrass theorem, this will have a convergent subsequence, right? But that's not the point right now. The point right now is that this sequence, as it stands, does not converge. So what that means is that we cannot break this up because that would be violating the assumptions of that limit theorem that limits respect products. However, that's not a proof that this limit doesn't exist. That's just saying this won't work. This method won't work. It's not enough to totally convince me that maybe there's some other clever way to do this problem. Right, so we'd have to be a little bit careful about that. But I will say this, I'm pretty suspicious that this does not exist. Because, this piece by itself doesn't exist, and this part here is converging to 3. If this had been converging to 0, I might have been thinking, well, that's 0 being multiplied by something that's kind of oscillating from -1 to 1, I'd expect 0 would be a reasonable answer. But here I got something that's wiggling between -1 to 1, and it's being multiplied by something that's kind of approaching 3. It's not approaching 0, it's approaching 3. So that's not, intuition-wise, that's not really making me feel too good. Okay, so here is what I actually would recommend that we do is that we take a stab at it that we think it doesn't exist. So I'm going to claim that this does not exist. Okay, it says compute the limit if possible. And I'm going to claim that this does not exist. And to prove this, let me just recommend that a good way to do that would be by way of contradiction. Suppose that it does exist. So by way of contradiction, suppose that this limit x plus 3 times the sine of 1 over x is equal to L. Let's just suppose that it does exist and it's equal to L. That'll be for some real number L. Okay. Now, if we do that, does anybody have any thoughts about? Now keep in mind that we know that this piece does not have a limit. This limit, just this part, does not exist. So again, I'm not going to break this apart because the product does exist. It equals L, but I don't want to assume that the individual pieces do have limits. But do you see something you could do?
In that sequence again.
We can use that sequence to show that just this part doesn't have a limit. But so let's just think about this for a second. So you're saying, let's look at 1 over n goes to 0, right? So then that would mean that if I plug that in over there, that it should converge to L. So if 1 over n goes to 0, then if we look at 1 over n plus, so now we're going to take f of that. We get something like this. And so this would have to converge to L. Right, for that particular sequence. And we know that this does not converge. Okay, this does converge. Right? The product converges to L. But again, I'm not quite ready to say what the issue is here. I'm not quite ready to have my contradiction. You're on the right track totally. That it's just the way it gets formatted. What I want to do, guys, is I do want to use the limit theorems, which means I have to have 2 limits that already exist, so that I can say that the third one exists, but yet I maybe know that it doesn't. That's how the contradiction can work. Do we have something else up here? on the board where the limit does exist for sure?
X plus 3.
X
The limit of
plus
x
three,
plus
yeah.
3, right? Exactly, we already know that the limit of x plus 3, so we know that the limit as x approaches 0 of x plus 3, that is equal to 0 plus 3, which is 3. And that you can just state again from your limit theorems. So this limit exists and this limit exists. That, oh, sorry. Right, these two limits both exist. So what can I do with the two? Divide them, that is exactly right, right? So by the limit theorems. The limit as x approaches 0 of the sine of 1 over x, that's what I actually am gonna get. This should be the quotient of the limit as x approaches 0 of x plus 3 times the sine of 1 over x, all over the limit as x approaches 0 of x plus 3. This is how you work this thing around so that you can use the limit theorems, right? So the one on top converges to L, the one on the bottom converges to 3. And now this is the contradiction, because we already know that the sine of 1 over n does not have a limit as x approaches 0. So this is a contradiction. So we do end up using the fact that the sine of 1 over n does not have a limit. So I'll just say since, and then I'm sorry, I'm gonna come over here. The limit as x approaches 0 of the sine of 1 over x does not exist. Something like that, again, if you remember that, oh, that was an example in class, you can just say, by an example in class. Just make sure it really was an example in class. I was there every single day, so I'm pretty sure I'll know if it was in class or not. At least I might have to look it up, but don't pull a fast one on me on that. But anyway, yeah, that's how that would work. So I like doing this by way of contradiction and then creating, it's sort of that 2 out of 3 rule. You've got one limit here, one limit here, and then their product is like the third one. If 2 out of 3 of them exist, then the third one must exist also by those limit theorems. And so to make that 2 out of 3 argument work, you have to assume that by way of contradiction, that this whole entire limit does exist. This is the whole idea here. Make a little bit of sense? Okay, good. So that's a little practice with calculating limits. Coming along pretty good. I don't have a lot more. I've got a couple more things here. Let's go on to number 13. So let's let f be a function from d to r. And I'm going to take c to be an element of the accumulation points of d. So take an accumulation point of d here. And let's assume that the limit as x approaches c of f of x is equal to L. And then what we're going to try to prove is that the limit as x approaches c of the absolute value of f of x is equal to the absolute value of L. So nothing too shocking about that statement. But let's see what we can do with this. So this is an unlike the last problem with the 2 parts of the last problem, this one is more abstract. We don't have a specific function in mind. So if it's more abstract, we're probably not going to be able to use the limit theorems. We might not be able to use any of our bigger theorems. Instead, what would we most likely want to do? Use the definition, exactly. And if I'm trying to prove that the limit of something is equal to something by definition, what does my proof start off with? Let epsilon greater than 0 be given. Rubber stamp it. Use exactly that sentence every time. And then I have to go over to my scratch work, potentially, unless you can see ahead of time how to do it. By the way, this is very similar to one that was on yesterday's homework, so I don't think you'll get too surprised by anything here. But it's on my sheet, so I thought, oh, I better do it. So what we're gonna do is we're gonna take the absolute value of the function that we are taking the limit of minus what its limit value is, and we want that to become less than epsilon. Okay. And does that give you any bells going off? Yeah, there's this modified version of the triangle inequality. If you take the absolute value of a difference, it's gotta be less than just the original, the absolute value of the original values before you took absolute value bars around them. So this one is less than or equal to this. This expression by the triangle inequality is less than or equal to this one. Right, so how do I connect these statements with arrows? It's only a backwards arrow, okay, so I was grading this problem actually, and some people were just doing double arrows on this. So this one only works backwards. And why does it work backwards? It works backward, it's a little confusing, because it's like, wait a minute, I thought this one was less than or equal to this one. So you sort of think of it as going from here to here. But you're actually going in reverse, because if this thing is the bigger thing, if this is the bigger thing and it's still less than epsilon, then the smaller thing would be less than epsilon as well. Okay, so this is the entirety of your scratch work. This is the entirety of your scratch work. So essentially, well, wait a minute, let's back up. We have to come up with a delta, right? You're gonna let it be epsilon, yeah, we're just gonna let it be epsilon, but guys, remember, we do have this assumption here that we need to use. How does this work? Well, if we already know that this limit is equal to L, then for any epsilon that comes across our path, there exists a delta already. So since the limit as x approaches c of f of x is equal to L, there already exists a delta. So actually, I don't know, Lila, let's be careful, we actually don't know that the delta is equal to epsilon. This delta is just coming from the assumption, right? So such that if 0 is less than absolute x minus c is less than delta, then absolute of f of x minus L is less than epsilon. But whatever that delta is that we just pulled out of the definition is the same delta that will allow us to now run the scratch work backwards, right? So with that same delta, what we can then say is thus by the scratch, I don't even really need to add anything else. We can just say, look, if 0 is less than absolute x minus c is less than delta, then by the scratch, absolute of f of x minus absolute of L, right, is less than epsilon. And that finishes our proof. I'm going too fast here. Is everybody out there in Zoom okay with this? Good? Okay. Yeah, so you find the delta from the assumption. We don't have any idea what it is, but there exists some delta from that assumption. And it just so happens that the same exact delta, right, then gives you what you want, because the inequality that you actually want to prove is easier than the one that you already got from the original delta. By the scratch work sort of shows that it's easier. to make that true. So that's kind of how that works. This would be a good test question, honestly. I mean, it's not that hard. It involves knowing the definition well of the delta epsilon definition and the triangle inequality, which is another important thing that we use a lot in analysis. So I think it's a nice problem, even though it may not seem all that sophisticated.
Would you want us to include that we use the reverse triangle?
I should probably have done that. So next to this arrow, I could just say, we are using, so we use. I'd probably just state it, you know, this triangle inequality fact here. Yeah. So that's helpful as well just to include that, I think would be a good idea. Okay. Does that feel okay to everybody? All right. Excellent. Let's do, so I realized. I might just do one more. Call it that. I realized that one of the other ones I have here was actually on your homework that we just did. So I might skip that one, and then the last one is just another one of these MCT things again. I think I feel pretty good about that. So let's just do one more. This one's a little tricky though, so it might take us a little thinking to get through it. So let's do this number 14. Let's assume that the sequence xn converges to x. And I'm going to let y be some other point other than x. Okay. Camera fixed here. Let's prove that y is not an accumulation point of this sequence. So I want to do something with accumulation points. This might just get the job done. So we do know, and we have proved that if xn converges to x, then x is an accumulation point of the sequence. What this is basically saying is it's the only one, right? The only accumulation point of, if you just have a sequence like 1/n converges to 0, the only accumulation point of that sequence is 0 itself. There aren't any others. Do you remember the homework problem where you were asked to give a set that has exactly 3 accumulation points? The reason that works so nicely was that you could just make 3 sequences, each of which would give you exactly 1 accumulation point. And that's how you got 3 accumulation points, by taking the union of those, right? So this is really just verifying that, yeah, if you have a sequence in front of you, you won't be able to have any other accumulation points aside from whatever the limit of the sequence is, regardless of whether x is actually one of the terms of the sequence or not. So the x might not be part of this set at all. 1/n being a good example of that. The 0 value is not part of the set, but it's the only accumulation point of that sequence. Yeah, so this is what we want to try to do. So I have to think about how to prove this. Let's just remember what the accumulation points of a set would be. Accumulation points of S, right? It's going to be the set of real numbers, right? So the set of X and the real numbers such that every neighborhood, so this is kind of the definition, every neighborhood of X contains a point of S other than X. So that's kind of the definition of it. But then there's also a proposition that we learned, and I think it's a worthwhile one. We did it in the group work actually, but it's certainly stated in the book. And that is, it's the set of X in the real numbers such that every neighborhood of X Everybody remember what this proposition said?
It's infinite many points.
Contains infinitely many points. Exactly, so this is another way to think about it. Infinitely many points of S. And I kind of like that way of thinking about it, to be honest with you. It's just, it's a handy definition to work with. So the accumulation points of S is, it's all the real numbers such that every neighborhood of X contains infinitely many points of S. Just to kind of help our intuition here, we might draw a picture. It's good to see you guys. We're on the last problem, actually. We're gonna finish a little early today. There's, what you have here, just to kind of give you a visual, you have a sequence that's converging to X. Let's just say X is right here. So you have all these dots kind of getting close there. And then if you take some other point Y, I don't know where it is, it could be over here actually. Let's just throw it over there. If you take any other point Y besides X, then Y is not an accumulation point of the sequence. That's what we want to prove. Okay. So one way to prove that Y is not an accumulation point of the sequence would be to find a neighborhood of Y that fails to have infinitely many points of the sequence in it. Okay, so that's an idea.
What's the value of y minus x over 2?
Let's look at Y minus X, right? The difference between those points. See, here's the idea. So you said Y minus X over 2, absolute value of Y minus X over 2. Yeah, so let me just start over here with the solution. Let's just take epsilon to be, the absolute value of Y minus X over 2. Of course, that's positive. Anytime you can make something that's positive out of your expression, that's really kind of helpful. Now, here's the thing. So I'm going to use the picture as my motivation. The picture is not the proof, but it's never bad to draw a picture. So here's Y and here's X. So Y minus X over 2 is just half of the distance between them. And I am going to make my neighborhood around X that way. And you know what that's going to do? That's going to suck up almost the entire sequence within this blue neighborhood. Right? After some n naught, there'll be some n naught value, and beyond the n naught value, all of these dots have to be in the blue region. And if they're in the blue region, guess what? They are not in this region. I can make a red neighborhood around Y that cannot have infinitely many points of the sequence because infinitely many points of the sequence are over here in the blue region. See how that works? I was gonna say, I'm looking at your face, so you don't look too happy. Let's try that one more time. Okay, I am using this, I'm trying to use, and this is a good thing to know, Alex, is that an accumulation point of a set has to have the property that every neighborhood of it contains infinitely many points of that set. This is a proposition, we did it in the group work, 3.4. So I've got a little picture here, and the idea is that if xn converges to x, right, then all of these dots are kind of coming over inside of this blue neighborhood. And we're going to make that neighborhood to have that radius right there. Okay, so by definition of this, right, there's going to exist an n naught such that beyond n naught, all of the terms of the sequence are in the blue neighborhood. And then what I'm going to do after that, I'm going to come back and make this red neighborhood. And I'm going to say, well, which of the points of my sequence are in the red neighborhood? And I don't know exactly which ones are in there, but beyond n naught, none of them are. Because they're all over in the blue neighborhood. As long as I make the two neighborhoods not overlapping. You can't be in two places at once, basically what I'm saying. Right? You can't be in both the blue neighborhood and the red neighborhood. So almost the entire sequence is going to be in the blue neighborhood. There will be only finitely many points, maybe the initial first few points of the sequence could be in the red neighborhood, but after a while, no more. Does this make sense? Let's see if we can write it down. I like this problem. So we choose that epsilon, and then since xn converges to x. Right? Then there has to exist an n naught, we already have the epsilon here, we're gonna use that epsilon. So there exists an n naught in the natural numbers such that if n is greater than or equal to n naught. Then absolute xn minus x is less than, here's my epsilon, I'll just go ahead and write it in. Absolute y minus x all over 2. Okay. So I am trying to disprove this definition, right? It says prove that y does not live in ACC of the set. So that means all I have to do to prove that y does not live here is I have to make a neighborhood of y right now. That means I need an epsilon for the y neighborhood. I'm trying to create the red one now. So what am I going to use for that?
Same one.
How about the same radius, right? How about the same radius? Because this is supposed to be right in the middle, right? So this distance here is supposed to be the same as that distance there. My picture is not perfect, but you get the idea, right? So I'm going to use that same epsilon, and that is a neighborhood. I've pulled that out of the sky. Here's my neighborhood I want to work with. Let's just see what points of the sequence it could contain, right? So so for n greater than or equal to n naught, the absolute value of xn minus y, how far are these terms away from y? I claim it is more than that same epsilon. We should maybe prove this. For this little step, I'm gonna give a quick reason.
Yeah, because I'm trying.
Well, let's just give a reason. So what if it was possible? Could it be possible for xn to be in both the blue neighborhood and the red neighborhood at the same time? Let's suppose that it was by way of contradiction, right? So by way of contradiction, if absolute xn minus y is less than absolute y minus x over 2, and we still have absolute xn minus x is less than absolute y minus x over 2. If both of these things are true, what do you suppose I'm going to do with them? To make my contradiction.
Between.
So can xn be this close to y and also this close to x at the same time? The left sides don't have to be equal to each other, like this xn, like x3, right? x3 is closer to y than it is to x. So I don't know that the left sides are equal to each other. What can I do with these two inequalities? Put them together, as in add them, right? As in add them. So that's exactly what I want to do. So then absolute xn minus y plus absolute, do you mind if I write that as x minus xn? Instead of xn minus x, less than, I got two of these. Okay, so doubling it, I get that. Now, what am I gonna use here? Triangle inequality, excellent. So triangle inequality, then I would know that xn minus y plus x minus xn is less than this thing. Right, because this one is less than this one. So if this was less than that, then of course this is less than that. What am I gonna do here?
So you get x minus y is less than x, or y minus x.
Yeah, I'm gonna clean this one up. Cancel the xn's, right? So that gives me absolute x minus y less than absolute y minus x, contradiction. Yeah, by way of contradiction, you cannot have the distance from xn to y being greater than, being less than. Actually, I should have, well, I made a little goof. I'm not gonna cream myself for it, but I should have said less than or equal to here. If I'm negating, if the opposite of greater than would be less than or equal to. However, it doesn't matter because this one is strict. This one is strict, and so when you add them together, it has to become strict. So the rest of the proof is fine. So let's just take a look at this. This is the key point. And so what is my final? How am I gonna finish this off, or do I have any room to write anything? I put it up here, I hope I have enough room. The neighborhood, I'm gonna call it, this is gonna be a neighborhood of Y. The neighborhood of Y going from Y minus absolute Y minus X over 2 to Y plus Y minus X over 2, right, that neighborhood. It's basically Y minus epsilon to Y plus epsilon, right? It cannot contain. Xn naught plus 1, Xn naught plus 2, etc. Can't contain any of the values when n is greater than or equal to n naught. So that neighborhood, that is my neighborhood, that is my witness that we are going to have a neighborhood that does not have infinitely many points in the sequence. It might have the first n naught-ish terms of the sequence, but no more than that. That's a finite amount. So this neighborhood, let's just call it Y minus epsilon to Y plus epsilon, right, contains at most, I guess it'd be n naught minus 1 terms of the sequence xn. And so by the proposition 3.4, by prop 3.4, Y is not in ACC of the set of xn's. It's running out of room. I'm kind of all over the board here. That seem okay?
So the reason is that there's a finite
Yeah, I created one neighborhood. I only have to find one. I found one neighborhood of X that did not contain infinitely many points of the sequence. And so that violates the proposition 3.4 for the accumulation points. Yeah. So I like the problem because it does make us use the basic information about accumulation points. I haven't seen a lot of examples of that, but this is a nice example of it. Everybody okay? I don't like, I have a couple more problems on here that I don't like, but I might make up a new one. Give you one more. I feel bad to quit too early. You see what I can think of. I want to do something with let's do this. So here's number 15. Let's assume that the limit as x approaches minus infinity of f of x is equal to L. And the limit as x approaches minus infinity of g of x is equal to infinity. Ooh, this is going to be interesting. And I'm just making this up on the fly. Okay, so if it doesn't work, don't blame me. Let's try to prove that the limit as x approaches minus infinity of f of x plus g of x is also equal to infinity. So the first thing you want to do is just, does this seem reasonable? Okay, so don't just launch into like blindly writing stuff down. It's okay to stop and think about it for a second. So notice that all of the limits have x going to minus infinity, so it's compatible with that. The f of x is leveling off at some, it's kind of like a horizontal asymptote at L, you can think of it that way. But the g of x function is blowing up, right? and you're adding them together, right? You're adding together something that's kind of leveling off roughly. I'm not saying it's perfectly flat, but it's leveling off as an asymptote towards L. G of X is blowing up. If I add two things together like that, I would expect it to be blowing up. The G of X is kind of gonna take over and cause the thing to go to infinity. So that seems reasonable? Kind of, I mean, if you need to, you can draw a graph, you know, so here's L. So as we go, maybe this is, as we go to negative infinity, this might be F kind of leveling off at L. And then as we go to negative infinity, G is, you know, doing something like that. Not quite vertical, please. It's basically going to plus infinity. And so then the idea is when you add them together, you would probably expect this. Okay, so before we actually prove this, I want to try to make a definition of what this would even mean. And I would probably ask you this as like a part A of the question, and then I would give you this problem. But the definition might be, you know, the limit as x goes to minus infinity of h of x equals infinity. I want to know what is, how do we like interpret that as a definition? So in this case, we're not approaching on either end of this, we're not approaching a particular point, right? So I would not start off with just expecting, you know, there to be an epsilon delta's traditional definition. It's gonna have to be modified a little bit. I might say something like this: for all alpha greater than 0, and that's gonna be referring to alphas that get as arbitrarily big as we want. There should exist, let's say, a beta that now I'm gonna be having the x's going towards minus infinity, so I would expect those to need to be less than 0, right? Such that if x is less than beta, then h of x is greater than alpha. Like that's what you would maybe expect the definition. Okay. Still making sense? Okay, so I'm gonna use that definition right here, right now, okay? So now I'm gonna start into my proof. This is what I'm trying to prove. The h of x is really just f plus g, okay? So what's the first sentence of the proof going to be?
Alpha greater than 0 be given.
Let alpha greater than 0 be given. Exactly. And my job is to cook up a beta from that. Okay. Now I can already find a beta for g alone. Right? But I've got two functions here, so you probably could imagine I might want to do like a beta 1 and a beta 2 or something like that, right? So let's do this from the definition. There exists a beta 1 less than 0 such that if x is less than beta 1, then g of x is greater than, now, anything we want to put here, right? Could be anything we want to put there. I'll tentatively put an alpha there, because that's what it says in my definition. But I got to be a little flexible about this, because there's also an f of x that involves L, and something tells me that that's going to have to come into my work over here too. Make sense? Okay, so now what about that part here? So what does this mean? This means that actually for all epsilon greater than 0, there will exist a beta 2 less than 0, right? Such that if x is less than beta 2, then absolute f of x minus L is less than epsilon. We can actually choose an epsilon value here because we're assuming that this limit exists and equals L. What's your favorite value for epsilon?
1.
I like 1. Let's do it. Let's do it. Okay, so we also know that there exists a beta 2 less than 0 such that if x is less than beta 2, then absolute of f of x minus L is less than, again, whatever epsilon we want, and I'll just go ahead and go along with that. Let's just choose 1 right there. Okay. So is this going to allow me to say anything about f of x itself? So this would imply that, if we remove the absolute value bars, we only make it smaller, right? So we could just, if it's true with absolute value bars, then without absolute value bars, it's even more true. And so this would then tell me, I'm gonna just solve this for f of x for a minute. This would tell me that the f of x is going to be less than L plus 1. And I want to know that because, f of x is part of my function here that I'm working on. Except I'm not real happy with this. By the way, I'm just winging this right now. I don't know if you realize this, I'm just making up this problem. And you're watching a mathematician try to figure it out, and like I'm not always getting it right the first time through. But when you read my solutions in Canvas, it was all so polished and beautiful. Of course, I sat there and figured it out for a while, right? Now I'm kind of winging it. And why I'm not happy, guys, is that I have figured out that g of x is greater than something. And I figured out that f of x is less than something. Now these two, and then you want to add them together, right? So you're adding together something where you kind of say, well, g of x is at least something. F of x is at most something, and so the inequalities are kind of going in the wrong direction. They're going in opposite directions, right? So comparing, by the time you add them together, they can almost kind of cancel each other out to some extent. I really want to get g of x greater than something and f of x greater than something, so that when I add them together, the result will be greater than something. I mean, ultimately, that's what I need to prove. I need to prove that f of x plus g of x is greater than alpha. So can we reconfigure this? Instead of saying f of x is less than something, I'd rather say that it's greater than something. Let's undo the absolute value bars here. You guys have helped me with this already once today. I'm just going to get rid of the absolute value bars. -1 less than f of x minus L less than 1. And if I want f of x to be greater than something, I don't want to work on the right side. I want to work on this part of it, right? So this is going to imply, it's not a double arrow because I'm going to drop what's on the right part and just focus on the left part. But this is going to imply that f of x is greater than L minus 1. Okay, now I'm feeling a little bit better about it. So there exists a beta 2 less than 0, such that if x is less than beta 2, then f of x will be greater than L minus 1. You guys with me? So then we can now go back and figure out a final beta. What do you suppose we want to choose for our final beta? The minimum, exactly. We want to go as far to the left as we can. So I'm going to take the minimum of the beta 1 and the beta 2. Okay, and then all I got to do now is just verify that that beta works. So let's assume that, by the way, we're going to run into another hitch in a minute. In case you all think it's smooth sailing, it's not quite ready to be smooth sailing. You'll see. So I'm going to assume that x is less than beta. That's what it says here. And then I'm going to look at f of x plus g of x. So then f of x plus g of x, I want it to be greater than alpha. Well, what is it greater than? Alpha for g plus L minus 1. Well, as long as L is at least 1, that will be greater than alpha. I mean, I really want greater than alpha here. But this L could be negative. It didn't really tell us anything about L. It could be positive or it could be negative. So I ultimately, in my proof, I need greater than alpha here. Right? And that would be just fine if L was, greater than 1. But as it stands, I'm not sure this is correct. So I need some help again. Can we change what we put up in this box, right? That's exactly the key idea. G of X is going off to plus infinity. So for all alphas, meaning not just this alpha, but any other alpha I wanna put there, I can make this argument work. Now, I do need the alpha to be, whatever I put up here needs to be greater than 0. So let's be careful. But what could we put here? Let's just tentatively put something here. Would it be like alpha minus L plus 1 or something? So if I change this to alpha minus L plus 1 for that, so the G of X, I'm doing these in the wrong order, by the way, guys, sorry, let's try this again. F of X is greater than L minus 1. And G of X is greater than alpha minus L plus 1. And that should give me equals alpha here, right? So that looks better. Now, my only problem is that, I mean, there's nothing wrong with what I've done here, but the thing is, the G of X is supposed to go to plus infinity, and according to this definition, for all alpha greater than 0, I can find a beta. Is this greater than 0? Because that, if
The absolute value though,
I could certainly,
or
I'd love to do that, but then I'll have to put it here
Yeah.
too, and then I'll have a problem.
Again.
I'll have the same problem again. So it's a little unclear that, so if. I mean, here's the thing, if alpha was a really big number, then subtracting the L and adding 1 to it wouldn't be a problem. Right? So what you could do, if you really wanna be totally sure of yourself, is you could just do something like this. I probably wouldn't make my test question like this hard. I'd probably start off with assume L is positive or something like that, just so it doesn't have to be quite so complicated. But like if you did this, now you've got something that's definitely, or maybe I don't want it to equal 0, maybe I just put a 1 there, right? So now I got something that's definitely positive, right? And G of X is greater than the max, so it's gotta be included in that is that it's greater than this. And so now, down here, saying that it's greater than that is fine, F of X being greater than that is fine, we get our alpha here. I'm happy.
We have to do the 2 cases, like 1 and alpha.
There's not really cases here, right? This is kind of putting 2 values together, but we're just taking the maximum, which means we're assuming they're both true at the same time. So we don't have to like prove it for this number and then prove it for this number, that's not how this works. Right, we actually have a single alpha value here that we're checking, and at any moment we can assume this, and the only reason for this part is just to make sure that the alpha is positive. Because if you just leave alpha minus L plus 1, it could be negative, because what if the L, you subtract L from alpha, maybe it comes out negative, right? If I did put this on a test and people just wrote alpha minus L plus 1 there, I'd probably just take it. 100% credit, and I wouldn't even mark off for that, because that's really just a technicality. Right, the concept of the definition is fine. I mean, in fact, you could even say here that this definition didn't need to be this way. Couldn't I have just said for all alpha in R, there exists a beta less than 0 such that blah 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 blah? That would work too. Yeah, you could have just weakened your definition to not insist that the alpha be positive to begin with. It makes sense to do that, because only positive values of alpha are gonna be interesting here to proving that H of X is greater than those values. But yeah, you don't really need to assume that alpha is positive there. So we could weaken this definition. Fact of the matter is, I have never defined this in class, so asking you to define this on the test would be a bold move on my part, because I've never presented it to you. And so then I'm sort of saying, I mean, if I ask you to make a definition of something, well, you can say, the definition of a chair is a fan, and say, that's your definition, I can't really argue with you, right? So, yeah, so it's a little bit of a bad question in that sense, but it's works great for the review session in terms of kind of practicing how you put these things together. So yeah, we've seen, I got inspired by that extra problem number 1 from the homework that you just turned in. Pretty much everybody did a great job on that. So if you see those kind of questions, f of x plus g of x, yeah, it won't be the first time, that's for sure. Any questions out there in Zoom land? Is anybody still in Zoom land? Oh yeah.
I'm
there's it.
still here, yeah, I'm still.
Okay. All right, well, I threw in an extra one. Free of charge, an extra practice problem for you to chew on. I think I'm gonna leave it at that in terms of the formal review, unless there's questions, if you guys wanna ask. So what I'm gonna do is, when I wrap this up, I'm actually having a belated birthday dinner tonight with a friend, and then I'll be back around 8 or so, and then I'm just gonna hang out all evening, and then I'll be back again tomorrow, by mid to late morning. But I can answer some questions before I go, if there are any.
Yeah, I do have one question.
1 second, Danny, I've got Litzy here with a question too.
Just for number 12, you know how we use the huge remark? For
Yes.
the huge remark, it says C has to be in the domain and it has to be an accumulation point in B. So are we able to use it even just without knowing that it's not an accumulation point, or should we?
The domain of this function is everything except -2. So the accumulation points of that are gonna be the entire real numbers.
Oh,
So that reminds me, if you have any dense set, what are its accumulation points?
everything.
All real numbers. Yeah, that was a group work. One of those, there's 3 or 4 group works that we have here to look at, and that's one of the items from one of the group works. If you take any dense subset, its accumulation points will be the whole real number line. Because if you take any real number, every neighborhood of it is gonna contain, because of the density, it's gonna contain points of that dense subset. Yeah, so, and in that case, your domain is everything except one value. So if you take, this would be a nice test question. If you take the real numbers and you just remove finitely many points from it, right? It's still gonna be a dense set. If you remove 1 point, it's still dense. If you remove 1 more point, it's still dense. Remove 1 more point, it's still dense, and you can do that finitely many times. Yeah. Even if you do it infinitely many times in some cases. Actually, that would be a question. Take the real numbers and remove any countable subset of the real numbers. You're still left with a dense subset. This wouldn't be good for this midterm, because this midterm is not about countable sets and density so much. So don't worry, I'm not.
Stop freaking me out.
I'm gonna get you guys are gonna stop asking questions, but inspire me to have ideas. Hey, Danny, what was your question?
Yeah, my question is for MST, what is like some applications or examples you can use them in? Because the only thing I can really find is like to prove BW theorem, but that's really it.
That's really what its purpose is. So the purpose of the monotone subsequence theorem, and I know that makes sense to ask me that, because we've seen lots of examples using the monotone convergence theorem, where we prove that it's bounded and monotone, therefore converges. So then the question is, well, what about the monotone subsequence theorem? That's the theorem that says that every sequence in R has a monotone subsequence. So I don't have any, other than using it in the proof of the Bolzano-Weierstrass theorem, we haven't really seen any good applications of it. I would have to think about how to create a question for that. I don't have one off the top of my head.
But you can ask me the theorems.
But I could ask you what the theorem says. Yeah, so I don't have a good answer for you on that, Danny. I'll think about it while I'm at dinner. How about that?
Okay, thank you.
If I come up with a good one, I'll send it out. I'll let you know.
All right, thank you. All right,
Okay.
bye.
No problem. Okay, I'll stop recording on that, and I've got to